Hello everyone, in this lecture of the topic linear differential equations, today we are going to learn how to find the particular integral when the right hand side function is the polynomial function. So this is our next shortcut method. So let us see how to find the particular integral. So this is the third special function, which is f of x is equal to x raised to m. M is any positive integer. So in this case, yp will be given by 1 upon phi of d x raised to m, because our f of x is now x raised to m. To obtain particular integral in this case, polynomial function case, we have to recall the Maclaurin series formulae for the few functions. Which are those functions? Let us see. We want the Maclaurin series expansion for 1 upon 1 plus t, which is 1 minus t plus t square minus t cube plus so on. And the second expansion that we require here in this case is 1 upon 1 minus t is equal to 1 plus t square plus t cube plus so on. So these two expressions, mainly these two expressions we will require in this third case. The important thing that we have to keep in mind in this case is that whatever term here we have written 1 upon 1 plus t, in that this constant term must be 1 only. So it must be there, then and only then we are going to we will be able to use this expression. Now we'll come to our term 1 upon phi of d. So we want to express this phi of d in the same form as either 1 upon 1 plus t or 1 upon 1 minus t. How that can be done? Okay, so here I am giving you the formula how it will be done. So 1 upon phi of d, it can be expressed as, now there may be two cases, that either phi of d will have the constant term or it doesn't. So if it will have, if it don't have the constant term, then take the minimum power of d common from phi of d. And if it has the constant term, suppose say k, then take that k common from the phi of d, isn't it? So once we do that, our 1 upon phi of d then will be in the form 1 upon, if we take minimum power of d common, then 1 upon d raised to minimum power into 1 plus remaining expression, we call it as say psi of d. Okay, or if phi of d contains the constant term, then we will take k common and we left with 1 upon k into 1 plus psi of d. So for a time forget about this thing, d minimum or k, just concentrate on this 1 upon 1 plus psi of d. Now see, we have taken these two, one of the two things common, just to get the constant term 1 in the expression, because then only we will be able to use the previous formula. So as we expressed our phi of d in the form 1 upon 1 plus t, so here our t is psi of d. So replace t by psi of d, and hence 1 upon phi of d in that form will be 1 upon d raised to minimum or k into, see the expression for or the expansion of 1 upon 1 plus psi of d will be what? 1 minus psi of d plus psi of d bracket square minus psi of d bracket cube plus so on. So this is when we get 1 plus psi of d, and then we operate this expression on the given polynomial function. Once we operate this whole term on the polynomial function, then we will operate 1 upon d raised to minimum power. If k is there, then we don't have to do anything. If d is there in the denominator other than this term, then we have to simplify it further. This is the one thing. Or for 1 upon phi of d, depending upon the terms, it can also be expressed as d raised to minimum or k into 1 minus psi of d. Means depending upon whether phi of d is containing constant term or not, we have to take minimum power of d common or the constant term common so as to express our phi of d in the form 1 minus psi of d. So use the formula for 1 upon 1 minus psi of d, that will gives us 1 upon d or minimum d with minimum power or the constant term k into the expansion for 1 upon 1 minus psi of d, which is 1 plus psi of d plus psi of d bracket square plus psi of d bracket cube plus so on. This is very simple case when the polynomial function is there. Very simple one to obtain the particular integral. Now regarding this, we will note down a few remarks which are very helpful while obtaining the particular integral. So let us see those remarks. Remarks. If our m is equal to n, then the nth derivative of x raised to n will be what? N factorial. Second, if m is strictly less than n, that is n is greater than m, the power of polynomial function, then nth derivative of x raised to m is always equal to 0. That is for our n will be, in that case, then it will be either n plus 1, n plus 2 and so on. That is greater than m. In that case, the nth derivative of x raised to m will be always equal to 0. These things, they are very helpful in solving the examples related to polynomial function. Third case, if m is greater than n, then the nth derivative of x raised to m will be what? It is m into m minus 1 so on into m minus n plus 1 into x raised to m minus n, and which can be expressed as m factorial divided by m minus n factorial into x raised to m minus n. So these are the few things which we have to keep in mind. Now let us go to example, because there is nothing more in this shortcut method. So let us go to the example. Solve the differential equation d square plus d of y is equal to x square plus 2x plus 4. So auxiliary equation is, it is d square plus d equal to 0. So roots are d equal to 0 comma minus 1, and hence complementary function is c1 plus c2 into e raised to minus x. This constant term c1 is corresponding to the root 0. So this is the complementary function. Now we will go for finding particular integral. General formula is 1 upon phi of d of f of x. Here phi of d is 1 upon d square plus d, and f of x is x square plus 2x plus 4. Now see here, this phi of d, it do not contains the constant term. So whatever formula we have discussed just now, according to that, we have to take minimum power of d common. Here minimum power of d is 1. So we have to take d common, so that yp it will becomes 1 upon d into 1 plus d. So see, in this way we bring 1 in the denominator, so that we got the form 1 upon 1 plus d. So using the expression of 1 upon 1 plus d, we can write it as, so our psi of d is d. So replace psi of d by d in the formula 1 upon 1 plus psi of d. So yp equal to 1 upon d as it is. Expression for 1 plus psi of 1 plus d is 1 minus d plus d square minus so on. Purposefully here I have not written the higher order derivatives whose power is greater than 2, because the highest degree of the x is 2 in the given function. So therefore, as per the remark, we don't have to consider the derivative terms greater than whose order is greater than the degree or the power of this x. So we have considered terms up to the same power, so that we will get the non-zero derivative. Now, so uh, of these infinitely many terms, we are going to consider only these three terms and we are going to operate them on this function x square plus 2x plus 4. These are very simple derivatives. Evaluate them. So the derivative will be, if we operate 1 on x square plus 2x plus 4, it will be as it is. Then if we operate minus d on this function, then it will be 2x plus 2. With minus sign, it will be minus 2x minus 2. And if we operate d square on this x square plus 2x plus 4, it will give us derivative 2. And if we operate d cube, d raised to 4, d raised to 5, all they will give us derivative 0. So we haven't considered them. Simplify this expression. So yp equal to 1 upon d x square plus 4. 1 upon d is the antiderivative, that is integration. So evaluate the integration of x square plus 4 with respect to x, which will be x cube upon 3 plus 4x, which is the required particular integral, and hence general solution is the addition of yc and yp. Therefore it is c1 plus c2 e raised to minus x plus x cube upon 3 plus 4x, which is the required general solution. So see how simple this example is. Let us see one more example. Solve the differential equation d square plus 4d plus 4 of y is equal to x cube plus 1. So auxiliary equation is d square plus 4d plus 4 equal to 0. Roots are, so which is the expansion of d plus 2 bracket square. Therefore roots are minus 2 minus 2. Hence, complementary function is c1x plus c2 as roots are real and repeated into e raised to minus 2x, which is the complementary function. Now, we will go to find particular integral. General formula is 1 upon phi of d of f of x. Phi of d is d square plus 4d plus 4 and f of x is x cube plus 1. Now see, here phi of d is containing constant term which is 4. So to get 1 in phi of d, take this 4 common from the denominator. So the expression will be 1 upon 4 into 1 because of this 4. So 1 plus d square upon 4 plus 4 upon 4, which is 1 into d. So our phi of d is now 1 upon 4 into 1 plus d square plus 4 plus d. So this d square plus d square upon 4 plus d is the psi of d, and we want to operate it on x cube plus 1. So use the formula for 1 upon 1 plus psi of d. That will give us yp equal to 1 upon 4 1 minus d square plus 4 plus d plus d square upon 4 plus d bracket square minus d square plus 4 plus d bracket cube plus so on. See here also I haven't considered the brackets having power greater than 3 because the power of x here it is 3. So we have to consider up to the cube only. Now simplify these brackets and collect only the desired terms that will give us the non-zero derivatives. So after simplifying it, we will be getting 1 minus. Now see here the powers of these d, capital D, they are less than 3. So we will consider both the terms from this bracket. Now square. If we simplify the square, one of the term will be d raised to 4 upon 16, as its power will be greater than 3. So we have neglected that, and then remaining two terms we have considered, which are d cube upon 2 plus d square minus, if we obtain the cube of this bracket, then definitely all the except in the expansion we will get only d cube term, and remaining all the three terms they will have the power greater than 3. So we have neglected them, and therefore we have considered only d cube term from this bracket. and further brackets will give us all the derivatives of higher order than 3. So we have neglected them because they will give us derivative 0 only. Now simplify this, collect the coefficients of these same ordered derivatives. So that will give us yp equal to 1 upon 4 1 minus d plus 3 upon 4 d square minus 1 by 2 d cube plus so on x cube plus 1. So now operate this operator on x cube plus 1 function. That will give us 1 upon 4 into x cube plus 1 minus 3x square plus 3 by 4 into 6x minus 1 by 2 into 6 plus 0 for all higher order derivatives. Simplifying this expression, we got yp as 1 by 4 into x cube minus 3x square plus 9 by 2 into x minus 2, which is our required particular integral, and hence general solution is given by yc plus yp, which is this expression, which is the required general solution. I hope you have understood this. Thanks for watching this video.